So this is the three-sum closest problem, which is very similar to the three-sum problem. In that case, we had to find three numbers which summed up to a value given to us in the target. In this case, the goal is slightly different. In this case, we want to find three such numbers who sum up to a value sum. This sum should be as close to the target as possible. Now, the goal is not actually to find three numbers, but to find their sum, which is close to the target. So, for an example, in the case of -1, 2, 1, -4, given the target 1, we know that the summation is 2. The summation of -1, 2, 1 gives the answer 2, which is as close to target as possible. No other combination would give you this close of sum. Now, if you thought about it for any time, one naive solution should be the first thing you'd think of. And it's the solution which says that, okay, let's have I, j, and k and three nested loops, and we'll just loop over every possible combination in order of n cube time, and that would give the answer. So we'll just sum them up after we have I, j, k and compare it to the target. That actually is a very decent solution to start off with, and we'll code it up. If you want to skip over it, you can look at the timestamps below, but we'll be reusing a lot of the code because I'm going to write it in such a way. Cool. So we'll continue writing this, and we'll start from I, going from 0 all the way up till n, not including n. Then we'll have j in range I plus 1 because we don't want to consider the same element again. Then we'll have k in range j plus 1. Again, we don't want to consider j again, and we'll go all the way up till n. The goal is to find, okay, let's have a temp sum, and we'll have nums of I, nums of j, and nums of k. Cool. The goal is to find a temp sum which is closest to the target. So we'll actually have an answer here, and let me initialize it with float of inf, and we'll keep answer as the minimum of answer comma temp sum. This, by the way, isn't exactly what we want to consider. We're storing the temp sum for sure in the answer, but how do you consider ans and temp sum? How do you consider if any of these numbers are any good? You have to compare it with the target and say the difference between ans and target is greater than the difference between temp sum and target. This temp sum minus target is smaller, so we'll store this. That's the goal here. So we'll have a key here, and we'll specify a lambda function taking the input x, and we'll return the absolute value of x minus target. And at the end, we'll return the answer. So now for a quick sanity check, let's do this. Cool, this works. The runtime would be a lot worse in large test cases because, as you can see, this is order of n cube already. Now let's talk about the first observation. The first observation is that we actually want the sum and not these three numbers. If we wanted these three numbers, the problem would have been a bit more complicated, but we actually just want the sum. What does this mean? This means that sorting the array should not produce any different results. Let me actually sort it right here. Okay. Now, sorting itself has very nice properties. You can do stuff like binary search on it, which, can you do it in this question? See, the goal of this for loop is very simple. Once you have I and j specified, I specified here and j specified here, in this remaining portion of the array, you could do a search. You could do a binary search saying that, okay, get me the number which is closest to the target. And you can use the same lambda function here to make your comparisons. Okay, if that seems a bit complicated, hold on for a while and I'll tell you even better solution. See, the goal of I and j was to specify two numbers, and once you have I and j specified, you can move around here. But you actually don't even need to specify j. You just need to specify I, and think about the solution greedily. See, let's actually code it up and I'll explain what's happening. Cool. So let's extract L and R, which we'll use for the search. Now this is no longer a binary search. That was sort of an intermediate solution. This is the optimized and the best possible solution. We'll have L and R is the two pointer solution. So we'll initialize L from I plus 1. So I is still going to specify something. We'll start from L I plus 1 all the way up till n minus 1, both inclusive. Cool. And while L is less than R, which always has to be the case, what do we do? See, now we have two pointers. We can move them about greedily. Let me actually access the elements here, nums of L plus nums of R, and we'll do nums of I for the temp sum here. I can't type today for some reason. Okay, fine. You have the three elements and there's some here. What can you make of this information? See, because of the fact that the array is sorted and because we're looking at things greedily, we can do a search here. What do we say? Okay, if temp sum is equal to the target, what does this mean? This means that these three have produced a combination which equals target, which is not just as close as possible to the target, it is the target. So the sum would be the target itself. Cool. What if temp sum is lesser than the target? This is where things become more interesting. Okay. Uh, let's actually imagine what's happening. We have L going from this side to this side, from left to right, and right going from the opposite side. So L goes like this, R goes like this. And the goal here is to move L or R depending upon its comparison with the target. So what if temp sum is less than the target? What does this mean? It means that the numbers provided to us sorry, are insufficient to reach the target. We are short of target, which means that we can increase the numbers here by increasing L, giving us a higher solution, a higher value of index. Higher value of index means a higher number because the array is sorted. Similarly, we can say that what if temp sum is greater than the target, which means that we have reached too far ahead, we have overblown our score, we are greater than the target, so maybe we should reduce the score now. Maybe we should decrease the R by 1. Now decreasing R by 1 means that we are also decreasing the number it's pointing to, again because the array is sorted. So we'll do R minus equals to 1. And at the end, what do we want to do? Once we have dealt with the increasing and decreasing of L and R, we also want to keep a track of what the best answer is. So we'll do a similar thing to what we did before. Answer comma temp sum. Again, the key is going to be a lambda function taking the input x, returning the absolute of x minus target. Okay, this should work. Let's do a sanity check. Cool. The runtime looks very bad. Actually, it's a good number, but it looks very bad. But I'll show you this gets accepted. So there you go. Let's talk about the space-time complexities in this case. This is, by the way, the most optimal case you can ever get. So this loop takes order of n time, and this loop inside takes again an order of n time. That's because we are not actually doing binary search here. We're just doing a greedy search. So L is going plus equals to 1 and R is going minus equals to 1. So again, this may like take the entire array to figure out the best solution. In fact, this will always take the entire sort of search. So order of n times order of n is order of n square. Space complexity is order of n again, is because merge sort is order of n. You could instead use a heapify function, which is an in-place algorithm, taking order of 1 space complexity. The time complexity remains the same. So this is it for the solution of three sum closest. Thanks for watching.